Hello, and welcome to another lecture, this time on autonomous equations, just section 1.6 in the book, and you can get the book for free at this URL. You can get it as a PDF, browse it on the web, or you can even buy a paperback copy. All right, so what are autonomous equations? So autonomous equations are differential equations of this form. Basically, you have dependent variable x, right, which is the quantity that we're studying as it changes in time. So we're trying to figure out what is x of t, right, x as a function of t. So we have the derivative of x with respect to t is some function that does not depend on t, right? It only depends on x. That's our equation, right? So that's what autonomous means, is that the right-hand side over here, this right-hand side in this equation, does not depend on time, right? So here's an example that we saw before. This guy over here, the Newton's law of cooling. We saw an example is cooling of a coffee cup, right? Now here's a very particular example. So A and K are constants. So in this case, K is 0.3 and A is 5, and we've drawn the slope field and a few solutions for a few initial conditions over here, right? So here the X was the temperature of the coffee, T is time, A is the ambient temperature, and K is constant. Now, the way that you can see that the equation is autonomous is that if I'm looking on a horizontal line here in this slope plot, right? The horizontal axis is the x-axis here, right? You notice that as I move between different times, so if I move in time, but for a fixed x, the slope is the same. It doesn't change, right? The only way that the slope changes is if I go up and down, if I change the x value. All right, now, as one of these solutions, this solution x equals 5 in this case, or x equals a more generally, right? That's a constant solution. It's just x is always a, or x is always 5 in this case, right? That's called an equilibrium solution. And it's basically, well, here, plug that in, right? X equals 5. If I do that, the right-hand side is 0, the left-hand side it's also 0 because constant derivative of constant is 0, right? So that's the solution, and that's basically what equilibrium means. I'm just going to stay at equilibrium forever, right? So it's constant solution. The constant solutions are called equilibriums, right? And they happen when the right-hand side is f of x is 0, right? Those are precisely the equilibrium solution. So in this case, it's only x equals 5, and you can sort of see it on this plot, right? I mean, if I start anywhere else, I sort of approach 5, but it's not going to be constant. I'm going to go, if I start below, I'm going, up towards 5, and if I'm going, if I start above, I go down towards 5 again, right? But it never stays constant unless I already started 5, and then I stay there. I don't do anything, right? So we're going to call such solutions, we're going to call them critical points. It's sort of like, in calculus, you call it, well, when the derivative was 0, critical point. Well, we're really saying, well, when is the derivative 0? So when it's x prime 0, except in this case, we're talking about sort of the function in terms of x. So it's a little bit different, but we're going to use the same language, right? So we're going to say it's critical point, and it really just means, that the equilibrium solutions come from the critical points, right? We just, that's the terminology. All right. Now, a critical point such as this one, in this particular case, is said to be stable because, if I start at 5, if I stay at 5, that's great. But if I now perturb, like if I hit the, hit the initial condition a little bit, right? because there's always some error. There's always, nothing is ever precise. Everything is always within some range, right? Now, if I start just a little bit above, so maybe let me draw this in a suppose that I just a little bit above, I still just stay at 0, right? Just a little bit below, I mean, not at 0, at 5, right? I still go towards 5, right? It doesn't change drastically. In the end, I cannot really tell the difference. What happened? That's what stable means, right? Is that if I change a little bit, nothing really changes, right? So, if think about, you have a little marble, right? If I have, a valley, right? And if the equilibrium is where the marble stays, right? So it's at the bottom of the valley, right? Well, if I hit the marble a little bit, it just goes back to its equilibrium position, right? So that's what means stable, right? Unstable would be the opposite, right? So, for example, if the marble was on top of a hill, I could balance, a marble on top of the hill. But if you hit it a little bit, it just goes off. It doesn't stay at the equilibrium position, right? So that's what stable and unstable means, right? So stable means that small change in initial condition, we're still going to get a solution approaching the equilibrium solution, right? All right. So let's look at something slightly more complicated. Let's look at the logistic equation, right? Which is like this. So it's very similar, except I have another root here, another critical point. In this case, critical point is going to be at 0 because I multiplied the right-hand side by x, right? So if x is 0, it's going to be a critical point, right? So here, k is positive and m is going to be positive. Now, this is a common model for population growth if you have some sort of a maximal sustainable population, right? It's sort of maybe a better model than the simple exponential model, which just says that everything just goes off to keeps growing exponentially, and that's really not the way it works in real life. Usually, you have some sort of maximum sustainable population. You cannot get over some population. So that's what this M is. All right. So here's an example, right? So we have here the maximum sustainable population is 5. The K, the sort of this rate of growth, is 0.1. And well, this is what it looks, right? So 5. This is the maximum sustainable population, right? And we've plotted a couple of solutions, right? And also the slope field, of course. Now, notice that generally, you would probably start between 0 and 5 here, right? Probably, if it's population, you definitely wouldn't start for negative numbers, but as far as the mathematics, that makes sense. It just doesn't make sense in real life. What does it mean to have a population of -5, right? That makes no sense. But so if you start over here, the population grows and then approaches 5, right? Because that's the maximum sustainable population. Maybe the maximum population in a fish pond or something. You cannot have more than some number of fish in the fish pond. Otherwise, it just gets too crowded. You don't have enough food, whatever. So that's what this 5 would represent, right? Now, if you put more fish in the fish pond than the maximum sustainable population, well, then you again approach 5. It's maybe not as good for the fish. They die off, right? Until you approach the maximum sustainable population, and then it stays there. Now you notice that this right-hand side over here has 2 critical points. One at x equals 0, that's because of this factor, and one at x equals 5, that's because of this factor, right? And those are precisely these, correspond to these equilibrium solutions, right? Now, x equals 0 is an unstable critical point, because you can see that if I start here, if I start at 0, the population stays at 0, right? It's, there's nothing to multiply, right? If the fish pond is empty, unless you put some fish in it, it's just gonna stay empty, right? It's gonna stay at 0. But the moment you put some fish in there, it will slowly grow to the maximum sustainable population. So it doesn't stay at the equilibrium, right? If you just nudge it a little bit, it goes to another equilibrium, right? It doesn't stay near where you started, well, I mean, it doesn't make sense for a population model, but as far as the mathematics is concerned, right? I mean, you could also nudge it in the negative, right? Have slightly negative x, and then it actually goes off to minus infinity, right? So x equals 0 is unstable, x equals 5 is stable, right? Over here, if I nudge it a little bit, I just approach x equals 5, right? So that's a stable critical point. Now, by inspection, just by looking at it, and it's clear that, well, no matter where I start, I sort of know where I end up eventually for very large t. So basically, we're looking at the limit as t goes to infinity. So if I start at something between 0 and 5, right, I end up at 5. If I start at 5, I clearly end up at 5. If I start at something bigger than 5, then I end up at 5, right? So basically, anytime I start anywhere positive, eventually I'm at 5, right? No matter what, because if I'm between 0 and 5, I keep going up and I approach this equilibrium, right? And if I start above 5, I go down, right? Because all of these lines are pointing down, right? And right, so that's what this means, right? That if the initial condition is positive, eventually I'm at 5, right? Now, at 0, when the initial condition is 0, well, I stay at 0. I mean, that's the equilibrium solution. So the limit is just going to be 0, right? And so that's what happens when the initial condition is 0. If the initial condition is negative here, if I start slightly below 0, somewhere over here, then you can see what these solutions are doing. They just go off to minus infinity, right? So either the limit doesn't exist or it's minus infinity. Now, it's actually not enough to decide exactly what happens when x is negative, because we don't know if if this x of t, if it will exist for all time. I mean, it might actually go to minus infinity faster, right? That might be like a vertical asymptote, right? So it might be that it just doesn't exist because x of t doesn't exist for all time, right? Maybe it does, maybe it doesn't. We can't quite decide from this picture, right? So, but it's clear it's going to minus infinity. We just don't know when it gets there. If it's as time goes to infinity, or if it as time goes to some finite number where there's a vertical asymptote, right? We don't know, but it's one of the two. All right. Now, from this, we see that we can actually decide what happens long term. So what happens for very large t, more or less, without needing to solve. I mean, we did not solve this equation, right? So there are certain questions, namely this long-term behavior, what happens eventually, that where we don't really need to know the solution, right? We don't need to actually find an exact formula for x and then take the limit in that exact formula. That would be much, much harder. It's much easier to just look at this picture and you immediately know what's going on, right? So, so what's the procedure? Well, it's enough to look at the so-called phase diagram or phase portrait. If we're trying to look at the long-term behavior. So, what is this? Well, we draw the x-axis, which is vertical. Then we mark the critical points, which is basically solving f of x equals 0, right? Solving the roots of f of x. And then we draw an up arrow where f is positive and a down arrow where f is negative. All right? So let's do an example. But I could do the example that we just did, right? So here f of x is this guy on the right. It has two critical points, x equals 5, x equals 0, right? So we drew the vertical x-axis, right? I drew little lines at these critical points, right? Those are going to be the equilibria, and then in between I put in the this up or down arrow based on the sign of f. So, for example, when x is between 0 and 5, f is positive. So I put an up arrow. When x is bigger than 5, then f is negative, so I put a down arrow. When x is negative, then f is negative, and I put a down arrow, right? And you can see how that corresponds to the slope field, right? Negative means all these lines are going down, right? Positive means I'm going up. Negative means I'm going down, right? And I have my equilibrium solutions over here, right? So just from drawing this diagram, I can decide on what happens given an initial condition. So, for example, if the initial condition was x equals x at 0 equals 3, then I know 3 is between 0 and 5. So I start in this range, and I have to follow the arrow up to 5 because that's the critical point, right? So I follow it up to here, right? And that's what happens to the solution. I don't know how fast it gets there. I don't know the solution. I haven't solved this equation, right? But I know what happens to x as t goes to infinity, right? So, and it's really, enough to first find the critical points, so solve this equation, and then figure out these arrows, which, well, you can graph this function, or you can just plug in, right, a few points, right? So, for example, if I plug in 6, so something bigger over here, it's negative. Now, f is, this thing, it's continuous. So, if it's going to be, between any two roots, any two zeros, if it's positive somewhere, it's going to be positive everywhere between those two roots, right? So I know that it's 0 at 5 and it's 0 at 0. And so if I check something above 5, I get negative. So it's definitely negative everywhere out here. If I plug in 1, which is between 0 and 5, and that's easy to plug in, you get 0.4, and that's positive, right? So I know that in this range, I'm positive. And if I plug in something negative, let's say -1, I get minus 0.6. And so that's this range, and it's going to be negative, right? Just because once you have 1 point, once you know it's going to be negative at 1 point, it's going to be negative in between those roots, right? Another thing that you could do is graph the f, right? Notice that this is, maybe let me put in the, a thinner line. So this is the x-axis, right? So the zeros are over here. Now, here, notice that maybe something somewhat tricky is that we are graphing y as f of x. So here, x-axis is the horizontal, and y-axis is the vertical, right? So it's opposite. Well, I mean, there is no y-axis over here, but the x-axis here is horizontal. Here, it's vertical, right? Because when we're graphing f of x equals y, well, x is now the dependent variable, right? All right. Now, from the graph, you can see that, this is where x is 0, this is where x is 5, right? You can see that for x less than 0, f of x is negative. For x between 0 and 5, it's positive. It's above the x-axis here. And then for x bigger than 5, it's negative again, right? So that's, that's how we get this this diagram, right? And so armed with the phase diagram, we can easily sketch solutions. Let me just, draw a couple. Suppose that, let's draw. Let's suppose that we had sort of a complicated one, right? We had. Let's suppose that this went up here, and let's suppose this also went up. This maybe went down. This went up, and let's say this went down, right? So this is our diagram. Let's maybe change the color a little bit. So that's our x-axis. Then we have equilibrium solutions are going to be these guys, right? Those are going to be exactly at the roots, right? Maybe change the color once more. And then, if we want to draw some solutions, right, that start in between the equilibrium solutions, well, suppose that I start over here. Well, there's an up arrow, so I'm just going to keep going up. And I know that I'm going to be approaching this equilibrium solution, right? It almost looks like it's going down. It's never going to go down. It's just going to keep going up, but it's going to approach that equilibrium solution. Over here, if I start over here, well, I'm also has to go up, right? So this is gonna look like this, right? If I start over here, right? Well, it's supposed to be going down, so I go down like this. If I start up here, I'm gonna have to go up like this, go down here, going to go down like this, right? So let's mark the. Let me do. Let's mark the which ones are stable, right? So this is a stable one because I keep approaching it, and this is a stable one because I keep approaching it, right? All the other ones are unstable. So maybe let's mark the unstables up here, right? So this one is unstable and this one is unstable here. I'm sort of, half stable. Sometimes it's called semi-stable. I go up here. I do approach from below. So if I start at this equilibrium solution and I nudge it down a little bit, it will go back to my equilibrium solutions. But if I nudge it up a little bit, it goes off, right? So that's not stable, right? Because, well, if I nudge it at least in one direction, it goes to another equilibrium, right? A stable has to be, no matter how I nudge it, I end up back where I started. Sometimes, again, this is called semi-stable. This one is fully unstable. No matter how I nudge it, it goes to a different equilibrium solutions. We're mostly just worrying about stable, unstable. All right. So that's basically what we did. So stable is if the arrows point towards towards the critical point from both sides, and it's unstable if you're in one of these three possibilities, right? Either it points away in both directions, or at least on one side, right? So those are going to be unstable, right? And so it's easy to decide which critical points are stable, which critical points are unstable, right? So this is just that remark about terminology. Sometimes these unstable guys are called semi-stable because, well, they're sort of like half stable, right? All right. Now, unstable points are generally would be sort of in a real applications would probably be bad news, because then the equilibrium solutions, it's hard to stay at the equilibrium solution, and essentially everything is always an approximation, so you're never exactly somewhere, so there's always a little bit of error, and for an unstable point a little bit of error moves you to a different equilibrium solution, right? So it's usually sort of bad news in terms of trying to predict something, right? Trying to predict what will happen. All right. Now let's do another example. Let's modify the logistic equation, and let's do logistic equation with harvesting, right? So it's just slight modification, which is going to basically move the critical points, right? So, well, the typical example of this is a fish pond or something like this. So decided to do something not so typical. So suppose that we're the fish pond. Humans are the fish, right? And there's an alien race that really likes to eat humans. And so then they keep a planet, let's say Earth, stocked with humans, and they want to harvest some humans to eat every year. But of course, they want to harvest humans and not have the humans die out, because, well, they would go out of business, right? So it's some restaurant, right, running this this business, right? So let's suppose that X is now the millions of humans on the planet, and T is time, and we can say in years, right? And M is the limiting population of Earth, or of this planet, when there's no harvesting at all. When you just leave everything as it is, that's what the limiting population would be, right? It would sort of naturally go towards that eventually, right? And K is going to be, again, just, how fast the humans multiply, right? So the equation becomes, well, it's this part of it, that's just the standard logistic equation, right? And now we're saying, well, we're going to take away H million humans per year, right? So that means that we want X prime, that's the rate of change, where, well, this is how it keeps changing, that's what's happening on the planet, and then we also are taking away something, right? So that's this minus H is our harvesting, right? All right. So now, what we do, we find the critical points, right? So that means we solve when is this zero, when is this right-hand side zero. If we expand it, we get this guy over here, right? And you notice that it's a quadratic in X. We're trying to solve for X equals 0. So trying to solve this equation for X, that's a quadratic. We have a quadratic formula. We can just plug in. And let's give the two solutions names. Let's call them A and B, right? And that's just plugging in the quadratic formula, right? It's the only difference is here is the plus and minus, right? It's the plus minus from the quadratic formula. Now, there's three possibilities. Either A, the guy with the plus, is bigger than B, Or we actually get a doubled root, right? That's would be when this right hand side. Well, this is 0, right? So plus minus 0, you get the same thing. Or when this right hand side is negative, well, this sort of discriminant is negative, right? What's under the square root, and in that case we get complex solutions, meaning we don't get any real solutions, and we're interested in real solutions. So meaning there's no solutions, no A and B, right? No critical points, right? So those are the three possibilities: A bigger than B, A equal to B, and there is no solutions whatsoever, right? Okay, so let's do an example. Let's suppose that M is 8 and K is 0.1 for simplicity, right? So here, let's suppose H is 1, right? So we have this equation out here. Well, this is what it looks like. This is what a slope field looks like, right? We have our two equilibrium solutions, and then it looks very much like very much like the standard logistic equations, but it's now at a slightly, these critical points, these equilibrium solutions are at different places, right? Normally the limiting position would be 8, it would be somewhere over here if there was no harvesting whatsoever, right? But now it's actually at 6.45, right? The lower one is also different. It's actually bigger than 0, the unstable, right? It's 1.55, so 1.55 approximately million, right? That's the unstable lower critical point, right? So we have these two critical points. The A is the stable one, the B is the unstable one, right? And we could even, if you let's do it with, let's say, blue, could draw the phase diagram would be this. There's up, there's down, there's up, right? And this is the A and this is the B, right? All right. So as long as there are at least 1.55, or at least B humans on the planet at some point, as we sort of go along, it will eventually will get towards A. The harvesting is unsustainable. This restaurant doesn't go out of business, right? So as long as at any point, it's at least 1.55 million humans, will eventually just go towards the 6.45, right? Now, if there's some big disaster, right? Maybe we're out here, and this equation does not deal with disasters, right? I mean, this is nothing bad is happening, but there was an earthquake, right? And it killed all these people. Suddenly we're down here, right? And then if we're down here, you notice that we just keep going down, right? So if there is a disaster, the population drops below this equilibrium point. It's the population drops to 0. I mean, mathematically, right? This equation will have this solution that keeps going down. But of course, if it's a population model, once it drops to 0, it's at 0. We're done, right? There's no more solution, right? But that's what would happen, right? So in that case, the aliens must become vegetarians, right? And it's not good for the humans either. I mean, they died out completely, right? So, but at least we got back at those evil aliens. All right. Now, what if the harvesting is 1.6? It's very precise, and because it is kind of precise. This is exactly this this situation where the two critical points were actually the same critical point. Right? So there's only one critical point, right? Which is going to be 4, right? So you're going to have this. This is A, B. It's 4, right? And notice that over here it's negative, so I'm going down, and over here it's also negative, so I have this. There, that's my phase diagram, and you notice that we're going, if we start above 1.6, we're going towards the equilibrium. If we start below, we're just gonna go back down to 0, right? So this is not a stable, it is a semi-stable, so not stable critical point. And so we get, that if the population starts above 4, then it will tend toward 4 million, right? You get these sort of solutions, right? And it will just tend toward, it will get closer and closer to 4 million, right? If we start below, right, then you just keep going down until you reach 0, right? So again, this has a problem, right? Because the moment there's any sort of disaster or something, the population will die out, right? Even if we sort of are, slightly above, we're sort of approaching the equilibrium from above, and then the disaster strikes. We nudge the solution a little bit, and suddenly it goes off, and everybody dies out, right? So this is an unstable critical point. Bad news for those evil aliens as well. Well, bad news for us too. Now let's see what happens in the third case when there were no solutions, so there were no critical points. And this is what happens, right? So in this case, suppose that we're h equals to 2, right? And our phase portrait, our first phase diagram just looks like this. There's no critical points, so there's no critical points to mark. And we're always, it's the arrow is always pointing down. And that's what happens to these solutions. They just sort of keep going down until they get to 0, right? So that can happen. I mean, there doesn't have to be critical points at all, right? In which case, you either keep going up or keep going down, always, right? So in this case, it's not sustainable. Population always goes to 0, no matter where you start. They're over harvesting, right? No matter how much they stocked the planet with humans to begin with, eventually no humans, right? So all right. So hopefully we're hopefully there's no we're in the h equals 0 case. All right. So that's that's about autonomous equations, or just some simple examples. All right, so I'll see you next time.